So while we're thinking about operations involving matrices, we also want to consider the product of two matrices. This operation will be very important when we discuss matrix transformations. To make the definition, we first recall that we can multiply an m by n matrix, A, by an n-dimensional vector, W, and we get an m-dimensional vector, W1, V1, plus W2, V2, plus ... plus Wn, Vn. If we think about a matrix as an array of vectors, it's natural to define the product of two matrices by allowing the left matrix to operate on each of the columns of the right matrix. So A times B is the matrix whose first column is AW1, second column is AW2, all the way down to the lth column is A times WL. Note here that the dimensions of our matrices are very important. Since our matrix A is an m by n matrix, we can only multiply vectors that are n-dimensional. The reason for this is when we multiply our matrix A by one of the w's, we should expect to get a linear combination of the v's. So this tells us that B must be an n by L matrix, where L can be any positive integer. We remember that when we take a linear combination of m-dimensional vectors, we always get an m-dimensional vector. That means that each of the columns, A times Wi, is also an m-dimensional vector. So the resulting matrix, A times B, has m rows and it has L columns. So as a handy device for remembering when we can multiply two matrices together, the inner dimensions in the product have to be the same. The result of the product will always be the two outer dimensions, in our case m by L. For example, if our matrix A is a 4 by 3 matrix and our matrix B is a 3 by 2 matrix, then the product AB of a 4 by 3 and a 3 by 2 is a 4 by 2 matrix. However, you cannot reverse the order of multiplication, because if you try to multiply a 3 by 2 matrix by a 4 by 3 matrix, you'll get nonsense. So to get a feel for how we would actually carry out such a multiplication, let's consider an example. So consider the matrix A with columns 4, 0, minus 3, 2, 2, 1, 4, 0, and the matrix B with columns minus 2, 1, 3, 2, and 0, minus 2. Matrix A is a 4 by 2 matrix. Matrix B is a 2 by 3. For dimension considerations alone, we cannot form the product B times A because the dimensions simply do not match up. We can only form the product A times B. The product A times B is a 4 by 2 multiplied by a 2 by 3 gives us a 4 by 3 matrix. This is a good thing to keep in mind as a sanity check, just to make sure that what you're doing makes sense. So the first column of our matrix AB is the matrix A multiplied by the column minus 2, 1. In the first row, 4 times minus 2 plus 2 times 1. In the second row, 0 times minus 2 plus 1 times 1. In the third row, negative 3 times negative 2 plus 4 times 1. And in the fourth row, 2 times negative 2 plus 0 times 1. For our second column, we multiply the matrix A by the column 3, 2. That's going to give us 4 times 3 plus 2 times 2, 0 times 3 plus 1 times 2, negative 3 times 3 plus 4 times 2, and 2 times 6 plus 0 times 2. And finally, for our third column, the first row is 4 times 0 plus 2 times minus 2. The next is 0 times 0 plus 1 times minus 2. Then negative 3 times 0 plus 4 times minus 2. And finally, 2 times 0 plus 0 times minus 2. The first column becomes negative 8 plus 2, 0 plus 1, 6 plus 4, negative 4 plus 0. The second column becomes 12 plus 4, 0 plus 2, negative 9 plus 8, 6 plus 0. And the third column becomes 0 minus 4, 0 minus 2, 0 minus 8, 0 minus 2. So the 4 by 3 matrix A times B is negative 6, 1, 10, negative 4 in the first row, 16, 2, negative 1, 6, negative 4, negative 2, negative 8, negative 2. So let's do one more example. So we have the matrix A, which has columns 1, negative 2, and 2, negative 4, and the matrix B with columns 3, 1, and 0, 3. Both of these matrices are 2 by 2 matrices. Since these matrices have the same number of rows and columns, we can multiply these two matrices in either order. So if we want to multiply A and B, that's a 2 by 2 multiplied by a 2 by 2 gives us a 2 by 2. BA is also going to be a 2 by 2 matrix. So let's compute each of them. When we multiply the matrix A by the column 3, 1, we get 3 plus 2, negative 6 minus 4. And when we multiply A by the column 0, 3, we get 0 plus 6, 0 minus 12. That gives us the 2 by 2 matrix AB, which has columns 5 minus 10, 6 minus 12. In the opposite order, we get, so as a word of caution, even if the matrix AB and the matrix BA are both well defined, they may not be the same. So matrix multiplication, unlike normal multiplication of numbers, is not a commutative operation. This particular oddity tells us that perhaps it might actually be valuable to take some time to study the properties of matrix multiplication and to really ask ourselves what sorts of properties that are familiar to us for multiplying real numbers carry over and which ones do not. We'll do this in the next few videos.